Hello everyone, I'm Andrea, and today I'm going to talk about the problem of network intrusion detection, and specifically in our work we approach the network intrusion detection problem from a sequential perspective, and we try to evaluate the advantages of sequential machine learning for network intrusion detection. So, starting from the problem, we live in a society extremely interconnected, where all kind of devices exchange data on some sort of networks. For this reason, networks are characterized by a large volume of traffic, high diversity, and low latency connection, as you might see from this slide. In these kind of networks, obviously, cyber attacks are perfectly hidden. So, in this kind of networks, network intrusion detection systems are a vital defensive system, a vital defensive mechanism. Traditionally, network intrusion detection systems inspect the traffic at the packet level. However, in this kind of networks, in nowadays networks, the inspection of single packets is hard and prohibitive. So to partially mitigate this problem, network flows were proposed as metadata about group of packets. So we can say that network flows are summary information about packets. And based on this definition, network flows has a limited semantic compared to packets. We are limited by this summary. So at this point, I might ask you, what is a pattern or a signature in network flows? And again, are there temporal relationships in network flows as there are in packets? And if yes, how they look like? Are they useful for network intrusion detection? To this end, to answer to these questions, we propose and we investigate whether sequential machine learning could provide some intuition, some insight to answer these questions, to ask these two questions. So whether temporal pattern exists in network flows as there exist in packets, and we try to also to understand whether this pattern, if it exists, are truly beneficial for network intrusion detection purposes or not. So this strategy to answer this question starts from the sequence creation process. So we need to apply sequential machine learning, we need sequences of network flows to learn temporal pattern from. However, without knowing what a temporal pattern is, we cannot create optimal sequences. And moreover, in network intrusion detection problem, it is even more challenging to create sequences and to extract temporal patterns, because we want temporal patterns among malicious activities. And malicious activities are really rare events. So this is extremely challenging. In literature, there are many proposals for creating sequences of network flows. We can group network flows based on the IPs, based on the IPs and ports, and many other rules. However, all these proposals do not guarantee to embed in these sequences enough information or all the necessary information to extract temporal patterns. Because these rules make sense for a human, but they do not logically make sense for sequential machine learning. And in addition, these rules do not address the problem of the rare event of the unbalancing between malicious and benign network flows. So we propose a different method to create a sequence of network flows, a really simple method. So we take a dataset, we actually use the timestamp to find time interval bounding attack type. So as you see from this picture, we find that time interval bounding the botnet, a botnet attack. And we use this time interval to create an attack scenarios, a botnet scenarios, where we include both the benign and malicious network flows in this time interval. At the end, after having identified all these time intervals, all the remaining network flows not containing in any time interval are discarded. So with our method, we address the two problems. One is we actually create attack scenarios where we include all the necessary information for extracting temporal patterns. And secondly, we also actually mitigate partially the effect of the masking effect of benign network flows by removing few of them from the dataset. So after having these scenarios, the sequences, we had to choose a proper sequential model to extract temporal pattern, detection pattern. And without knowing anything about the pattern, we decided to use long short-term memory as sequential model. The reason why we choose long short-term memory is that it is one of the most successful machine learning models, sequential models specifically, and it is able to adapt to different time scales based on the context. That is a really interesting property. And partially, long short-term memory solved the vanishing problem. That is a really tough problem for sequential machine learning models. And as you see from the slide, we use a particular version, a step version of a long short-term memory with 2 layers, so to let the model works at least with 2 different time scales for detecting and classifying network flows specifically. And in order to assess the performance of the long short-term memory, we have to define a term of comparison. And this term of comparison is a static model, a feed-forward neural network model, that actually classifies each network flows based only on the future, on the information within the network flows. So it does not have the concept of sequential. So it does not use what comes before these network flows. And in this way, by comparing the overall performance of the model, we can understand whether long short-term memory and sequential machine learning are indeed useful for network intrusion detection problem. At this point, I say you that this is nothing new. In literature, there are a lot of works using both sequential and static model. So we actually we slightly refine the question, and we ask, why should we bother in using sequential machine learning? And to answer this question, we look under the hood of the overall performance. So this is the difference in our work. If in this slide, in this example, I can give you 2 models, a long short-term memory and a feed-forward neural networks. And I say you that these 2 models have the same performance. Here you see the confusion matrix. And at this point, you would guess that the models are similar and their detection pattern are similar. But that's not true, because the overall performance just gives you an overall picture. If you look at the single prediction of the 2 models, you see that there are actually differences in static models and sequential models. But for really understanding these differences, you have to go down and not use just only the overall performance, but see the detection patterns. And to do that, we use an ensemble model, because it's not simple to analyze these detection patterns. We actually use a really simple ensemble rule that takes the models, the trained models, and use a logical OR operator to connect them. So at the end, if at least one model predicts a network flows as malicious, then the overall ensemble model predicts these network flows as malicious. The rationale here is that if the detection patterns of the models are different, then the overall ensemble has superior performance compared to the best performing model, because it leverages both the detection pattern of one model and the detection pattern of the other model. So in this way, we actually use this technique to really assess whether the detection pattern really differ. So here we are going to see a few results, and we start from the comparison between the long short-term memory and the feed-forward neural networks at the scenario level. So at the top you see the results of the long short-term memory, and in the bottom table you see the result of the feed-forward neural networks on one of our datasets. And in the two highlighted scenarios, the botnet 1 and botnet 2, there is an interesting observation, because you see that on botnet 1 the best performing model is the feed-forward neural network, and on botnet 2 the best performing model is the long short-term memory networks. But this is quite astonishing, because these models are extracted from the same interval. So these are actually one scenario split in two parts. And so this suggests that the models actually learn different patterns, and then the way you create these scenarios, these training sequences, really influences the models, the final model. The second observation here is on two completely different attack types, port scan and DOS slow lorries. Port scan is an attack type that generates large volume of traffic in really short time frames. And contrary, DOS slow lorries generates low volume of traffic in really long time frame. But despite these differences, the long short-term memory that used the concept of sequential relationship, temporal relationship, was able to adapt the time scale based on the context, and actually find a way to classify correctly both these different types, these two different attack types. You can see that the long short-term memory performance are at the same level as the one of the feed-forward neural network. So this suggests actually that the long short-term memory is indeed able to adapt the time scale. In this slide, we compare the ensemble, the overall performance of the ensemble, this table, with the long short-term memory. As you see in the middle of the table, the overall performance of the ensemble, and on the two columns on the right, we actually subtract the false negative of the long short-term memory from the false negative of the ensemble. So here you see that if there is a negative number in these rows, it means that the ensemble does better than the long short-term memory. And you actually see there is in the two highlighted scenario, there is a really quite huge increment in the performance of the ensemble. And this means that the ensemble actually takes advantage from the patterns of the long short-term memory, but also from the pattern of the feed-forward neural networks. So it means that by using both these patterns, the ensemble is able to do better than the single models. And this means that the patterns of the models are really, really different. And here we showed you only the comparison with the long short-term memory, but the ensemble has superior performance also compared with the feed-forward neural network. So the final message here is that the long short-term memory is really an important model even in the network intrusion detection domain. And actually, from what we saw, the long short-term memory led to different detection pattern in several scenarios compared to static models. And we saw also that the way you train sequential models is really important, and that our method was able actually to train quite well a sequential model. And finally, obviously, there are also limitations in our works, and we are aware of them. We do not actually mix up different attack types, and we evaluate few architecture. So there is much to do in future. Hope you enjoyed the presentation, and see you at the Q&A.